Okay, so welcome everyone again to the third part of the introductory video on CSG project. So till now, we have discussed about the first 5 components of the project. Now in this video, we'll be discussing the next two, task 2, processor design and system integration. So as I've been telling, processor design would be something new that you would be doing in this project. This is the main thing that the entire team should focus on, because this is where I like previous batch, like my seniors failed to complete them, complete it, this part. So once you complete the process design, I think the rest all would be easy to debug. So you can complete them easily. Process design will take more time, both for building, designing, and also debugging it. So let me use the process team slides to explain about the process design. So this was the presentation of our team, the process team, process sub team for the final CC presentation. Okay. So again, so a processor, the goal of this processor should be that whatever ISA that the team decide, the entire team decided upon, you have to design a processor that will be able to execute those instructions, whatever you have designed. So irrespective of what design choices you make, you should be able to design a processor accordingly. So when we talked about the instruction format, something like this. So this is already fixed. You would have already fixed this, like what are the first 4 bits, next 2 bits, these things. So based on this, you should accordingly process the instructions. So you will also be designing a processor in your CSD lab in using hack VHDL language, VHDL, a hack computer. So it will be similar to that, but this would be much more complex because you will be designing a pipeline processor. In the lab, you will be designing a single cycle processor. We designed a multi-cycle processor, and you will be designing a pipeline processor. So what my advice would be is that you first design a multi-cycle processor and then make it a pipeline processor. So that way you'll have a complete understanding of what is a multi-cycle processor and then pipeline processor. Directly, if you jump to pipeline processor, it might be difficult. It is easy to convert a multi-cycle processor into a pipeline processor rather than building from start, because we don't have any experience of building a pipeline processor. So the recording is going. Okay, so again, the instruction set architecture is what decides the design of the processor. So these are the instructions, just like you saw before, and this is the format. So how is the processor designed? Uh, so there are many components in a processor, which means there are many files in a processor. Basically, you can think them of as verilog modules: the ALU module, the control unit, the register file, the memory. So so you would be designing a module, maybe a part of a chip, like let's say part of a chip, which takes inputs, these things, input 1, input 2, like A and B, and the control bits. The control bits, so everything is every component will have the control from the control unit. So control bits will be the input along with input 1 and input 2, and there will be an output and some zero flag and negative flag. This is specific for arithmetic ALU, but everything will be what we call timed or controlled by the control unit. So I'll also explain what is a control unit. So let me just first explain how does this look. So you will find a register file. A register file is particular nothing but a register module, which takes as input clocks and is right. If you know how a simple verilog code looks, then inputs are clock and is right, whether to write or not. And A1, A2, address 1, address 2, and address 3. At a time, you will be able to read two values and write to one register. So the the working of this may look something like this. So the control unit is an FSM, basically a finite state machine. So it would transition to different states. So let's say the first state, like I would have learned this in pipeline like CO course. Let's assume there are 5 stages for an let's say ALU operation. ALU operation has only 4 stages. There is no memory stage. Okay. Let's assume we have an ALU operation. The first stage would be a fetch stage. The second stage would be decode stage. Decoding and the instruction getting back the registers, getting registers. The third stage would be the ALU operation, execute stage. The last one would be write back stage. So what happens is that you design the time period of each stage. So how much time will that take? So you would be designing that time to be the maximum of all such stages. So if let's say the fetch stage is faster and it takes 2 nanoseconds, and the decode stage is also fast, it takes 2 nanoseconds, and the ALU stage maybe takes more time, 3 nanoseconds, and write back stage takes 2 nanoseconds. So there are memory stages. There is different stages I will show you. So there are like this. This is a state machine. You see, there is reset, fetch, decode, mem address, execute R, execute I, execute register instruction or execute immediate instruction, branch, ALU write back, mem write, mem read, mem write back. There are 2 things. So if you see all these, there are different stages. So you would be if you have to adjust the clock such that all the stages get enough time for the values to settle down. So when you do an operation, so it takes some time for the final registers or the wires to set in that correct thing. So you have to let me tell an experience. So once we decided the clock, like we kept the clock very large time period. The clock is very slow. It would take, I think, 1 second for one instruction to execute. So we made that for debugging purposes to just monitor each stage, and we kept reducing the time period of that. We kept increasing the frequency to see whether the final thing will work actually. But what we realized is that when we keep on reducing the time period, we can do that in Verilog. We keep on reducing, but after some point, the output, whatever outcome that you come, whatever you see in the display or whatever values that are being written to memory and register, they are garbage values. They are not the values that you would expect to processor work. This is because there are few stages which require some time before they give you the final correct output. If you see there are critical paths. Like what is the critical path is the path that requires largest time. So if it is a graph, something like that from start to end, so the time required to travel will be the largest one. So you have to wait at least that much time before you could expect the result to be correct. So we couldn't reduce the frequency after some point. I think the speed was 300 megahertz, if I'm not wrong. 300 megahertz, I think that's what I think, the speed that we could achieve. So you cannot reduce that below that. If you reduce, there will be some stage which will get less time. So you have to make sure that so you will know that initially you can just keep on a safe side, you keep a very large time period and then keep on doing that. So if you see register file, so if you see this state is some variable or some register, for example, now in the verilog code, the control unit verilog code, there is a variable called register. There is a variable which is of type register whose name is state. So what you do is at every passage, depending on the current state. So if you are in fetch state right now, the reset state is the first state when you start the computer. That is only entered once. There is no indirect just see reset. So currently you are in reset. Computer has started just right now. So when you say passage, so you write the FSM logic. I am in current state reset, and so which means that I have to go to fetch state. You directly go to fetch state. Now in the second passage of the clock, you would see, so I'm currently in fetch state. And you will see what is the PC value pointing to. So you will then direct this PC value to here. The ROM is nothing but the place where the code is located. You'd send this, you would say the read signal to be 1. Till then, the read signal would be 0. Next, you would say the read signal to be 1 because you are in fetch state. What is the address that you give to this as input? That which would be the address of the PC, the current PC value. So the display address, I'll leave it for now. I'll explain again. So is write is 0. Register write, like instruction register write. So should I write to the instruction register, the register that stores the instruction, the 32-bit instruction? So that would be 1. Byte write would be 0. Byte read would be 0. Address would be PC. You'd connect these things. So you'd be selecting a bunch of bytes, you'd selecting address. The PC you will connect to address, and display address, keyboard signal, ignore this. Keyboard register, ignore this. So because IR write is 1 and address is PC, before you go to the next clock cycle, you'll be writing such a logic in the memory module such that based on these inputs to write this data, IR display data to output. So in the next clock cycle, you would have the instruction in the IR instruction register. So for which you'll go to decode stage. So while in decode stage, you can be sure that the IR is having the current register. So simultaneously in each fetch state, you would be setting few control flags and then transitioning to the next state, decode. So in the next passage, you would be in decode stage, at which point you'd be setting those control flags such that the instruction gets decoded, and then you'd be transitioning to the next state depending on what you decoded. So to do all this, you require that one clock, like passage and negate, one time period. So to do this, so based on the complexity of the task, the time period that you require to complete that stage before the next passage, you'd be adjusting that. So control unit will have conditional things. So all these things would give these are the opcode, function code, RD, these are from the IR. So these are the different fields in the IR. So based on this and based on many other inputs, the different flags would be set. So if you are currently in decode stage, the memory write, memory read, ALU, you will set all those flags to 0. They'll not work. They'll be just idle. That's what is multi-cycle processor. A multi-cycle processor will take different number of cycles for different type of instructions. When you design pipeline, then the logic will become complex. You will have to have multiple control units. Control unit will be divided. If there is only one control unit, because at each time only one instruction is being controlled. If there are many instructions, each instruction will have its own FSM currently working. So that's what you will be doing. So if you see accordingly to the current state and next state, you will be setting these flags and then working accordingly and then working. So these are the different modules. I will not show the code explicitly for this processor because that would actually make it worthless. Like you not be able to truly enjoy the building of. I'll just show one code, maybe a register file, just to tell you how it looks. Like I'll explain the register file completely, right? So these are different modules, memory module. And this is the complete architecture. So this is the micro architecture. So there are two things you have to know. Architecture is ISA. Like when you say architecture, you define the instruction format. When you say micro architecture, it is the chip or it is the wirings or like the processor that is going to execute that particular architecture. So this is what complete architecture is. This is from the book. So I'll show the book. I'll again go through the book. So if you see, there are many things. This is PC and this is address. You'll be selecting address, whether the instruction to fetch the next stage is what is pointing by the PC or what is pointing by the result of the previous instruction. So when this will happen is when you jump instructions. So when you jump, you'll not be fetching PC plus 4 in the next time, the next processing time. Next instruction would not be PC plus 4. It would be the instruction that you should jump. So based on that, you will select this. So the logic of what to select is in the control unit. Depending on the previous instruction, you have to store every information. It's an FSM, remember. So based on that, you'll be setting the clocks for the next time. And everything will have a clock. See, the common thing that happens all the time is the clocks. And these are boxes and these are registers. So when you see this, these are registers. And there is this extend thing, which will extend a 24-bit value. If you saw that, like the ALU operations have 12-bit, 12 or 11-bit immediate values. So this particular component will extend it accordingly. And also there are 24-bit immediate values for jump instruction. Those will also get extended accordingly. Negative values, those will also get extended accordingly. So all this logic is done here. And this is the register file, ALU. That's it. Beta memory. So this will not. This doesn't include the display and keyboard components. That thing I'll tell you next. So there are many challenges that are faced. Like they wrote this memory size constraints. Yes. So when we try to make the memory, like there are two kinds of memory. I think DRAM, block RAM, and then some other RAM. So the difference was that like continuous RAM. I think that's I am calling it continuous RAM, but I don't know the exact term. The difference is like this: a block RAM can be read only the reading is clocked in a block RAM. The writing is always clocked. When you say write this value, the write will not happen directly. You have to clock it. You have to clock, and only at this point, at this passage or at this negate, you write that value to this particular location. So a write is always clocked. But depending on whether the read is clocked or not, the memory size, you'll be able to use block RAM. So the thing is, if you want continuous read, which means that as soon as I change the address, the read value should change. If it is even low, if it takes some time, it has to change. I don't have to clock it, so I don't have to give a separate cycle to read that. You can assume that when you give this address, by this next clock, the output will be something like this. There is no intermediate clocking. So if you want that, you can use block RAM, which is a separate part of the chip. So you understand, right? So if you want continuous read, then you will be using LUT. So basically the chip has LUTs. That's what like I don't know the name, the full form, LUTs. There are 6,000 LUTs. So when you design, when you write the verilog code, that verilog code, like whatever you use, the NAND gate, OR gate, MUX, registers, wires, those are all finally are LUTs. So when you say wire, there'll be a kind of wiring in the LUTs. When you say register, they have a separate kind of LUTs. So LUTs is what is used up when you keep on increasing your code. So when you include even memory inside that, the LUTs will be, you have less LUTs. You cannot use that for processor, other things. So that's what we got. Like till midterm, where we didn't include the keyboard code, till then, we were having enough LUTs because we are using a LUT memory. We are using continuous memory. The design was easy. When you use continuous memory, I think there was no complexity in designing the memory part when reading the instructions and also writing to memory, both instruction memory and data memory. But once we included keyboard, the number of LUTs is exceeding. We cannot implement that in the small board that you have. So what then we did is that we learned about the concept of block RAM and learned that there are at least 240 KB of block RAM, 200 KB of block RAM, which you can simply use. Till then, our memory size was only 16 KB or 20 KB. So after learning about block RAM, we used block RAM. We changed the entire design. That now there are two. So if you see this, both ROM and stack and heap space RAM, these two are built using block RAM, and this display memory is built using uh, the, the continuous memory LUTs. So this is because display memory frequency is very high. The HTML frequency is very high. If I make it a clocked read, I think it would not work. I didn't even know how to do that. Like we didn't even know how to do that. So we just used the continuous RAM. So the other two we used block RAM. So IO devices, how do you convert in the IO devices? Race conditions. There were few design in this design. If you see, there are few race conditions. A race condition is where if you do something like if you try to compute something on a clock cycle on a POSIX, so where the output will affect the input. So what will happen then? So will the previous input gets computed, or the output gets computed again back? So if you search, you can see the race conditions. So there are many race conditions which are still in the design, but they work perfectly because of the lag. So when you do a computation based on the input, if it is very fast, that the output is not going to the input. So the time that it takes for the output to affect the input, if it is very large, then the time that it takes to compute the input and give the output very soon, then you will not have a problem with it. But that's still a race condition. Just that the time difference is very high, that you will not have a problem. So how to clock different components. So, and also ALU and sign numbers. These are some challenges. Okay. So this is their presentation, and let me show you like the best part of like what helped more. Like so here we have single cycle processor, multi-cycle processor, pipeline processor in this book. So this book is really helpful. So whatever design we did is something of a the base design is like something like this. So this is the base design in any architecture. If you search like a verilog code for ARM processor, then you'll see something similar to this. There will be memory, register file, data memory, ALU. They're very similar to that. You'll not find something different from that. So this is a single cycle processor. So you can follow this book. This book only tells you about that. So you have to use your programming. Like this is like a pseudocode, not even pseudocode. You're just explaining the solution. You have to implement. There are very implementation challenges. Here they told that PC as source. So we required many registers to do. We required many clockings. Like we included many clock the components other than in addition to whatever they provided here. And here we wrote register, right? What is it? Is it a wire or is it a register? I think you should find out. So one point is that when we designed the thing is not working because we didn't know the deep meaning of what is register and what is wire, where to use register, where to use wire. So there are many basic things that you should keep in mind while designing the processor, because those will play a very important role. When you come, you'll soon like maybe at a later point you'll realize that no, this particular thing should not be a wire. It should be this particular variable should be a wire, or wire. It shouldn't be a register, or it should be a register, or it should not be a wire. Something like that. We have to keep in mind all these things, and I think you'll be able to do this. And they also explain so this is the logic. If you see in this book, they have the complete logic. So when you are in fetch state, so this is the controller. You will set the address source to 0, ALU source A to 1, ALU source B to 10, ALU up to 0. And when you will move to decode stage. So depending on if memory op equal to 0, 1, you'll move to memory address. If data register op equal to 0, 0, and function if I is 0, the fifth bit of the function is 0, then you go to executor. So this is the logic. This is simple FSM. So you have to write the code. By seeing this FSM, you should be able to write the verilog code. You should have to practice verilog code, and also you have to go through the basics of digital design. I think in this semester you'll having a digital system design course. Again, I think by Janaran. So Dr. Janaran, you can talk to not talk, but you can ask sir also different things. Maybe go through the lab exercises. just to warm up your verilog skills and this system design. You'll also using verilog only in that lab. So again, pipeline processor is also here. You can use this. So the hazards, I think you should be able to do this. Let me just show. So this is the code. ALU, there is ALU.p, encoder.p. Encoder is for keyboard. Incremental build.p. This is the top module. I'll be showing. What shall I show? Register file. So again, one good thing is that you'll be using Vivado. 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 So Vivado is what you are going to use to do all this. So again, one thing, I think you should go through the development videos. There are many, what we say, sample projects. Try these sample projects. I very much recommend you trying these sample projects. So you'll get to know the different what to say yes. You'll get to know the different you get to know about the environment. So install Vivado. Yeah, I think I would recommend using the computer lab system. They are much more powerful, and this Vivado is a very big application. It takes up, I think, every time I use Vivado, fan would be running at full speed. So it's a highly computation intensive task. So try using the computer lab systems. If your laptop is not that powerful. So there is this blinky. This is the first thing that we tried. So it just blinks. There are very lights. So if you see this is a board, how it looks. So there are many. So there are many things here. There are switches. There are these PMODs and the aux cable, like you hear, right? These buttons. This is the chip. This is the ARM chip, I think. I think one is ARM chip and one is the programmable chip. We have Ethernet also. You have two HDMI ports, HDMI in, HDMI out, and you have this power cable and USB also. So you have many things. There are lights. So the blinky example will actually show you how to write the simple code that will make the light blinking, like for every half a second or 1 second. So go through this. There are many stages here. So you have to first, if you know, if I will show you. There are three things: synthesis, implementation, and bitstream. So you can like every time you do a like the project, you have to first synthesize the design, and then implement the design, and then program the board. So there are three stages like this. So what we did is, when you write a Verilog code and you try to simulate it, there are simulations after. So after whatever you design, like entire code, you could simulate it even before synthesizing. That's a simulation based on the code. And after you synthesize, the code will get converted to some other form, a form where it is implementable. And you can again simulate this. And after that, you implement the design, the next step. And again that you can do a simulation. So after every step, there is simulations. The reason being is that when you go from one stage to other stage, the conversion rules will make the meaning of the code maybe separate, like different. So like let me tell you, one design what we did, it is working perfectly fine before synthesizing. As soon as you synthesize the design, there are many things. The optimization, it's an optimization. So the Vivado will optimize your Verilog code to a format. So it will remove unnecessary wires. It will remove unnecessary registers. It will even remove components that you don't know. And if you again try to synthesize and see what is the design, you will see many of the components removed. You will see many of the components getting wired differently, not working properly. So it will try to do all those things. It will try to change the meaning of the code itself. So when you synthesize again and simulate again, all the simulations will happen inside the code only, in the this thing only. So when you simulate again, the output is not the same. So which means that your design is not synthesizable. That's what you have to learn. Whatever design you put, that is only simulatable. It's not synthesizable. So you have to make a design that is synthesizable. So we did this. Like it took 2 days to realize that something that the code that you did is not synthesizable. And then we made few changes. We did the complete documentation. What is the reason that this particular line of code is not getting synthesized properly? Because there is a style of coding also. So when you do in a digital system lab, there is no style. You write just like a C program. It works still. You only use delay something. There is some delay timeout. You'll use many constructs of the Verilog that will make your life easier. It should make the writing code easier. But though you cannot use those things. So it's not like a C programming. It's different from C program. It's a different thing. So you have to write a synthesizable code. And then once you synthesize and then you simulate, okay, everything is working fine. Finally, the Fibonacci number in the register 2 is correct. That's what we tested. The first program that we tested is register 1 will have 1, register 2 will have 1, and register 3 should have 2. And we'll copy back. And then after every loop, register 3 should have Fibonacci numbers 1, 1, like 2, 3, 5, like that, 8. So that was the code that we are testing. So and we saw all the signals are getting correctly done, and all the reads are getting fine before synthesis. And after synthesis, it's not well. It broke. The control unit broke. It keeps on getting into fetch state or fetch, decode, fetch, decode, fetch, decode, fetch, decode. Something happened, like it's not working. So make sure that once you make that is simulating before that, and then modify the code so that it is synthesizable. And after that, even after synthesizable, it is not implementable. So there are few race conditions or some timing delays that keeps on getting more and more, that the clock timing is getting different. So these were the exact challenges that our seniors faced. They told that there will be timing errors when you try to implement on a board. That is the reason they told that it's not implementable. A processor is not implemented in the chip because there will be timing errors. Those are not timing errors. Those are just the design flaws that they made. So try to make your design implementable, synthesizable, and then implementable. And after that, the generation of bitstream is simple. You can generate and then program the board. I think you will find a few difficulties while installing the Vivado. Try to use Ubuntu board, Ubuntu system, Ubuntu login, not the Windows. Install the Vivado, and you'll be also find some few difficulties when you program that. So you have to detect actually the board. You'll be able. There is a part where you have to detect the board. When you connect the cable from both to board to laptop computer, the board should get detected. So I think we debugged that. We use few like the Xilinx as what we call Q&A forum. We searched that and then did something, and then it finally was to we installed few packages or removed something. I don't remember, but few challenges. You'll find few challenges while using Vivado. But if you follow these things and then this, you should be able to do. So you see this don't touch, right? This is what like when you say some parameter to be don't touch, then it will not be removed by in the synthesis or implementation process. So it will directly convert. It will not try to optimize this particular variable. We use that just to see whether is it the reason that this particular variable is getting removed. We found that that's not the reason. So again, we commented that out. Even if you even remove modules completely, if you don't connect this input and output to any other module, this module gets completely removed. It will not get removed in before synthesizing, but it will get removed afterwards. So we have to see. So if you see RT1, RT2, register address 1, register address, okay. So the value being read by address 1, address 2. The input is clock. The input is right, whether to write or not. Address 1, address 2, address 3. So address, whatever address that you give in A1, the value in that address will be going to RT1 and A2 to RT2, and whatever value that you give here, write data, will be written to this address 3. And this output LED for debug purposes. Like what we did is when we tested Fibonacci, when we presented in checkpoint 3 presentation. checkpoint presentation, what we did is to demonstrate that our processor is working. We connected this LED to register 3, like I told the Fibonacci program, and then it showed like, and then when we run the process without display and keyboard, the only way to verify the processor is something is that since it is connected to register 3, it will first show 4 bits. It will first show 2, and after some time, it will show 3, and it will show 5, 8, which means that the register 3 is getting the right value. The LEDs are just showing the register's value. We use that things, and they have two internal variables like storages. One is the register file, and I is dummy in there. So register will have, there are 16 registers, and each register is it's a 2D array. How do you declare a 2D register variable? So initially, even before everything, every register file will be having value 0, and the register file 4 will be having 32 value. I think this is again for debugging purposes we did this. And always at POSET, if isWrite is true, then register file A3 will get the value write data. Simple. And I think we're assigning these values to LED, and assign RD1 to register file A1, RD2 to register file A2. That's it, end module. It's a simple module, register module. So this is simple. If you see like the incremental build top keyboard and control unit, and even ALE is also simple. Control unit, you see that's much more complex, a very big code which you'll be coding. So these are the different things in the processor design. So mainly follow this book, try to do this, and also try to search simple ARM code. Like you can for just verilog code for ARM processor. GitHub, in GitHub, try to search in GitHub. CPU implementing verilog. Try to see this. I see the again same like register.v multiplexer control unit. So I'll just show this control unit. I think it would be something similar, something small. So this is a simple control unit. This is small. So this is how you use a control unit. You can, I think it will be difficult for you to test this, but you can use this for understanding purposes. Everything ALU source, all these control units, everything will be same most of the time. Like in every code, you can use that. So that's the processor design part. The next part, again, which is very challenging task, is what is this? System integration. So system integration would be the fun part, or what we call is the important part. Is like even if you design everything, you have to show and get the input, right? At least show. No, not at least. You have to do both of them. It's mandatory. Like we did. Like now that's the benchmark. You have to have display and keyboard both working. So the HDMI protocol, you have to see this HDMI protocol. How does a HDMI work? What is the protocol of the HDMI? So there are 10 outputs in HDMI. So what are those 10 outputs? So study all this. So you have to know about the HDMI protocol. So when we design, we have to go through the HDMI protocol. We have to write the separate component, the separate sub-chip that will handle this HDMI protocol. So how this works is like this. It's a memory mapped IO, which means that the content to display will be in memory. That's what is memory mapped IO. Or the input that you get will be stored again back to memory. So the only thing is that the processor will do, like I'll show right. So whatever you want to display, you write that to display memory here. So you want to display white, black, 4 bits. Let's say 4 bits. You write that 4 bits to starting location in the display memory. You write the entire thing, whatever you want the screen to look like, in row major order. Assuming that the screen is a matrix, in row major order, write those bits into this display memory. So the part of display component is that it will have a counter, or it will have a counter which counts from this point in the row major order until this point, and then goes back again here. keeps on counting. So the only task of the display memory, it will keep on reading memory from top to bottom like this, the display. So memory is linear, so it will keep on reading this, and then according to whether the particular bit is 0 or 1, it will send the HDMI signal to be black or white. That's what you have to program. It's a simple display, but the thing to do, the logic, how to write a counter counting from this to this, and based how to read that memory. It's a continuous memory. That's a hint. That's the revelation actually. I'm revealing that. So how would you read that? 0. If it is 0, how would you do that? So to be like, we couldn't actually design that completely, because I'll show this website. This website, again, we have to, the process design team and both of them should try all this. Like this is a very helpful website. It will show FPGA programming, and you have HDMI here. So it explains. So this one explains the entire HDMI protocol. They explain the HDMI protocol. They say this is what we are looking at, a 640 by 480 screen, and what is a signal, TMDS skill, time, these signals. This is the code. So they provided everything. So try to read this, and you should be able to achieve this. And you will not be able to achieve this because this is a generic code, and you have to use separate code to these things. And when we tried this code, doing many changes, doing many clock times, we couldn't get that. We couldn't get to display this. Once we achieve this, then the code here, like what is that? The code that is making this pattern. This is the code, right? This is the code. There is some always. So this is the code. There are 3 wires, RGB, right? RGB, like like for white, you'll have all these 3 things to 1 1 1 1. All as for white, it will be completely full, and 255 255 255, and black 0 0 0 0. So the red wire will get, if the counter x 50 and counter x is less than something, some logic, it will be 0 0. It will be 0 0, or else it would be, so it would be this value and or this value. So that's that logic. So this logic will get replaced by, if the particular memory, if the counter is 0 and the first bit of the first byte of the memory address is 0, then it would be 255, or else it is 0. That's the logic that will be written. And this is the counter. If counter equals to 799, if the counter has reached end, the counter, there are 2 counters, counter x and counter y. One x will go vertically and y will go horizontally. So if the counter is 799, then it is 0. If counter is 799, then counter y will become, again, this is increment logic. If counter x is, if you are in the last line, then counter y will be 0. If counter y is also at last, or else it will become counter y plus 1. That's it. If counter is equals to 0, it will happen. This is, for all the things, the counter is will be incremented. So this is the logic. So it's, one second.